Um, Hello, everyone. Welcome to the afternoon session of our first webinar on the Educational Outreach Program on Small Diameter Copper Tube Fin Heat Exchangers. We are already a couple of minutes into the hour. We're just waiting for to see if there are more attendees coming in, but I guess we'll go ahead and start this. So again, welcome. Before we actually formally start, just a few announcements. One, we will keep all the attendees muted. So if you have any questions, comments, suggestions, please type them in, and then we will address them at the end of the presentation. In addition to that, so the slides that we'll present today and the actual recording of the presentation will be available to you as of tomorrow, along with a feedback survey that we highly encourage you to fill them out. Again, for those who are interested in getting a sample heat exchangers for testing, we require that you attend all 3 webinars and fill out the feedback survey. So again, I highly encourage you to do so. So everything will be available to you tomorrow. So I'm going to get started. Okay. So first, introducing ourselves. For those who are not familiar with us, OTS, or Optimized Thermal Systems, is a company that stemmed from the Center of Environmental Energy Engineering from the University of Maryland as a proprietary R&D outlet for the sponsors. So though in nature, our projects and research are very similar, but we're 2 very separate organizations. But we also have exclusive license to the general purpose software developed at UMD, where we can customize in-house. Our partner, International Copper Association, we have a strong partnership working on several projects, focusing on heat exchanger design using small diameter tubes. And Copper Alliance is a large organization that pushes copper for markets on broad applications, sustainable development initiatives, health, and the environment. So let me introduce myself. My name is Daniel Bacellar. I'm a PhD in mechanical engineering from the University of Maryland. I have recently joined OTS, and I have here with me my colleague, Dennis Nasuta, who helped me put this webinar together and giving me some technical assistance during this presentation. So here's our contact info. Again, you will have access to this information again tomorrow. So in this presentation, there are 4 main parts. One, the introduction, then fundamentals, a more fundamental approach in the small diameter tube heat exchangers, actually small diameter tubes, and then we'll move to a heat exchanger design. And lastly, I will present some applications and some numbers for everyone to have a feel of such application. In this background, the first couple of slides here, since the program was intended or targeted for a broad audience, from students to experts in the field, so we're trying to be able to address everyone. So the initial slides, probably the majority of you are very familiar with it. It's very elementary, but I would like to keep it on record anyways. So let's start with the definition of a tube fin heat exchangers and the main parts. On the left-hand side, we have here a figure of a tube fin heat exchanger cut open, where we can see the tubes, the fins or the extended surfaces where the air flows in between the tubes and the fins, and the refrigerant flows inside the tubes, as indicated by the arrows here. On the right-hand side, we have a nomenclature, just for record, for your information. I'm not going to spend time on this, but once you have your material in hand, you can always refer to this regarding the parameters naming that we use. Now, tube fin heat exchangers, we have 2 main parts. We have tubes and fins. So starting with tubes, in particular copper tubes, and why we are interested in having copper tubes in our heat exchangers, some of the interesting properties and characteristics. We have high thermal conductivity, which gives us low thermal resistance in the wall, thus facilitating the heat transfer between inner and outer fluid. We have additional advantages in terms of corrosion, biofouling, and antimicrobial properties, which from a heat exchanger context is more to reduce the material buildup and potential fouling that can block the fluid flow and therefore degrade the performance over time. In addition to that, copper tubes are a soft metal, pliable, so there's ease of inner grooving. Inner grooving, I mean those grooves indicated by the image here on the upper right corner. Now, if we combine copper tubes with small diameters, we have some further advantages. Small diameters, we will end up with thinner walls. Thinner walls means a even lower thermal resistance because we're reducing the distance between inner and outer fluid. And the second one, in particular for high pressure systems such as CO2, small diameter tubes with thinner walls can withstand those high pressures using less material than conventional diameter tube heat exchangers. Now, let's just briefly introduce fins and enhancements, and why do we have fins? So on the left-hand side, we have here a tube bundle, finless or bare tubes with a subscript BT, and we have the air flowing across the tubes, and the heat load can be calculated based on the overall heat transfer coefficient, the surface area, and the delta T. Now, if we look at the envelope or the space occupied by these tubes, when we add the fins, we have not only the tube surface area, but we also have the fin surface area. So the fins, for the same volume and envelope volume, they provide us a significant amount of surface area, and therefore we get a much more compact surface. And by that, we have the gain in terms of heat transfer by adding the surface area as indicated by this equation. So the primary reason why we have fins is to provide us with additional surface area. On the right bottom side, we have the most common external fins. We have flat, wavy, louver, and slits. And on the left-hand side, we have in-tube, the most common tubes, have smooth and inner grooved. So we talked about fins providing area, but we can improve even further the heat transfer by adding enhancements. And enhancements we can understand from the in-tube side by the microfins or the grooves. And from the fins or the air side, we have these two types here, louvers and slits, where we can see these cuts. And what they do is basically increase the U. So the fins, they provide surface area, and the enhancements, they provide higher U. And therefore, we increase even more the heat load. Okay, so that was a very elementary and basic introduction to tube fin heat exchangers. Let's start with the motivation and what drives heat exchanger design and pursuit for better heat exchangers. So we have a tripod of energy efficiency, environment and safety, and cost. So we're obviously focusing on improving COP, reducing billing costs and primary energy use. But on the same side, on the other side of the hand, we have direct refrigerant emissions, carbon footprints, end-of-life equipment, and natural resources, and obviously cost of manufacturing, tooling, and shipping. So when we tie all these three together, we have a push for better and smaller heat exchangers. So we have this worldwide push for more efficient heat exchangers, and based on what we saw in the initial slides, it seems like we have everything figured out. How can we get more efficient heat exchangers? Let's add fins and enhance them and enhance the tubes internally. What happens nowadays is that we basically have reached the limit of the state-of-the-art tube fin heat exchangers can do. So the solution to push for more efficient heat exchangers is overall sizing increase. So we're increasing the surface area while also increasing the volume, not necessarily increasing the compactness of these heat exchangers. So over time, what we're seeing is a gradually enlargement of these heat exchangers, which obviously affect the shipping and space issues. They're more expensive, heavier, they consume more refrigerant charge, and they will obviously be oversized for many operating conditions, which can reduce the system's performance. So the purpose of this educational outreach program was to provide the professionals in this area with new design approaches for heat exchangers where we can actually have more efficient heat exchangers with more compact surfaces without having to increase the size of these heat exchangers. And we have significant benefits from it. And by doing so, we can do so by reducing the tube diameter. So the four main objectives of this presentation is provide some fundamentals on small diameter tubes and how it impacts the performance, the potential reduction in size of the heat exchanger, and the amount of charge or refrigerant in the heat exchanger. Then we're going to move on to the actual heat exchanger design challenges, considerations. And third, I would like to discuss the importances of accessible and inexpensive design tools for small diameter tube heat exchangers. And lastly, present a few example cases where the three above objectives were successfully applied. And though this presentation is mainly theoretical and more explanatory, the last session, I will show some very interesting numbers. So just for you to have a taste of this on how small diameter tubes can positively impact the performance of these heat exchangers, we have 70% material cost reduction with more than 50% charge reduction and even reducing 60% of pressure drop. So these are some numbers that we actually we found by optimizing heat exchanger for actual real applications. So let's start with the fundamentals. And the first slide that I have here is the first order analysis, and it's called first order analysis because there is no performance assessment of any kind. It's just a geometry analysis and the impact of the tube diameter on three important metrics. So we have on the y-axis the airside surface density or compactness, which is defined as the overall surface area divided by the volume or the space occupied by the heat exchanger or the surface. The second one on the contour plot, we have a very similar metric called material utilization, which is the surface area divided by the material volume. So instead of the volume occupied by the heat exchanger, is the amount of material that is required to get us that amount of surface area. And the third one is the internal volume. The internal volume indicates the amount of refrigerant that we can get, that we will have in the heat exchanger. And what we're seeing on the x-axis is the tube diameter, and the two curves here are for finless and fin tubes. The purpose is not to compare one and the other, but how they change with respect to the three metrics above described. So we can clearly see an increase in compactness as we reduce the tube diameter, and obviously we have a very steep increase in the compactness as we go below 1 millimeter. But again, we also have a significant reduction in material required for the same surface area as we reduce the tube diameter. And lastly, indicated by the size of these symbols, is the internal volume. So if we go from 10 millimeters all the way down to 3 millimeters, we have a significant reduction in refrigerant charge. But why am I showing this? What do we know? This is what we know very well, and this is what we have been doing for quite some time now. This is the state-of-the-art tube feed heat exchangers with diameters above 5 millimeters. Now, we have a growing interest in actually designing these heat exchangers with tube diameters below 5 millimeters, around 2 millimeters, as I'm indicating here. I have this additional image here of a microchannel, which is the counterpart or the competitor of a tube feed heat exchanger, that though it's situated somewhere here in this plot, it does have some disadvantages that we'll discuss further on, and why we should pursue the tube feed heat exchangers with smaller diameters. And the last region, what I'm calling the future generation of heat exchangers, and we're obviously going over time towards that direction. But the future generation of heat exchangers, though it seems theoretically pretty good, it's still very costly and very challenging in terms of manufacturing. So we don't have technology readiness to manufacture such heat exchangers. But we do have a technology readiness for manufacturing tube feed heat exchangers with small diameter tubes in the group or the region that I'm indicating over here. And that's where the purpose of this program is focused on. Now let's talk about the performance, and starting with the airflow thermohydraulic characteristics as we change the tube diameter. So now I'm not talking about heat exchangers, but from a fundamental aspect of the tube diameter itself. If we look at the relationship between the non-dimensional numbers, especially Nasuta and Reynolds numbers, if we derive the above equation, one will find out that the heat transfer coefficient indicated by H is inversely proportional to the hydraulic diameter of the tube. So the relationship is hydraulic diameter to the power of m minus 1, where m is usually a number between 0 and 1. And why does that happen? When we look at two different diameter tubes and we have a flow across these tubes with the same velocity but different diameters, what happens is in the small diameter tube, the absolute thickness of the thermal boundary layer is actually smaller than it is for the larger tube. And the implication to the thinner thermal boundary layer is a higher temperature gradient at the wall. And the heat transfer coefficient is directly proportional to the temperature gradient of the wall, because it indicates the thermal diffusion between the wall and the tube. The tube and the fluid. So we have a higher local heat transfer coefficient across the tube surface with small diameter tubes, which gives us an average higher overall heat transfer coefficient. Another interesting aspect of this is that since we have the same velocity, the Reynolds numbers on a small diameter tube is smaller, than the Reynolds number is also smaller. Therefore, the separation point occurs a little bit further on the surface. So we have a relative larger surface or effective heat transfer surface on a small diameter tube compared to the larger diameter. And why are we comparing same velocities? Because in the heat exchanger context, we usually have similar phase areas and similar flow rates. So the actual airflow velocity across the tube bundle is very similar regardless the tube diameter. But even if one asks, no, from a fundamental aspect, what happens if we compare them in a dynamically equivalent flow condition or the same Reynolds numbers, then for the same Reynolds number, the smaller diameter tube would have a much higher velocity, and the heat transfer coefficient is directly proportional to the velocity. Therefore, it increases even more. So what this is suggesting and showing is the heat transfer coefficient is primarily a function of the hydraulic diameter of the surface, and the flow regime will basically dictate the intensity to which the heat transfer coefficient changes. And though this looks very nice, and from a thermal perspective, that's what we're getting out of reducing the tube diameter, regardless the airflow velocity. But there's no free lunch. There's also a similar relationship between the friction factor and the hydraulic diameter. If we look at the same relationships, the friction factor increases as we reduce the tube diameter, and the reasons are very similar. If we have the same velocity, the momentum boundary layer is also thinner at the small diameter tube, giving us a higher velocity gradient at the wall. And we know that the friction factor is directly proportional to the velocity gradient at the wall, and therefore we have a higher friction factor. If we increase the velocity, however, though the friction factor reduces, but the pressure drop, the overall pressure drop actually increases, since it's proportional to the velocity to the power of 2. Now, what this is showing is that though we've reduced the tube diameter and we have a higher friction factor, we do have ways to manage how to potentially get lower pressure drops with higher heat transfer coefficient. So this is one of the challenges and considerations that we need to employ in our heat exchanger design when using small diameter tubes. And then we need to find a sweet spot between the thermohydraulic characteristics. Now, just to give some numbers as examples for dry air on a flow across a tube bundle, finless tube bundle for constant velocity and constant pitch ratios, okay? The x-axis is the tube diameter, and the left y-axis we have in blue the heat transfer coefficient, and the right y-axis we have in red the pressure drop, and in green the ratio between the two. So what we're seeing here is that by reducing the tube diameter, we have a significant increase in heat transfer coefficient, though we also have an increase in pressure drop, But if we look at the ratio between the two, we're still benefiting from a tube diameter reduction, since the heat transfer coefficient increases faster than the pressure drop. Now, another example, an interesting example, because in this case we have a tube and fin, and the behavior is a bit different. So from a heat transfer coefficient perspective, it's behaving as we expect from what we discussed in the previous slides, though the pressure drop doesn't have the same kind of trend that we saw for the previous case. And what we're seeing here is actually a reduction in pressure drop, increase and reduction again. And there are reasons for that, and this is one of the things that we can leverage and play with when designing small tube fin heat exchangers. And to that matter, if we think about reducing the tube diameter, the relative fin surface area contribution to overall heat exchanger actually reduces. So on this plot, what I'm showing here is the fin to tube surface ratio. So this is the ratio of the fin area over the tube surface area as we change the tube diameter. And we have a linear relationship as we change the fin density here. But in any case, by reducing the tube diameter, the contribution of the fin reduces. So this have obviously an impact on the pressure drop, maybe positive, because we saw that we can potentially even reduce the pressure drop even though we have a higher friction factor over the tube surface. On the other hand, we also have some less contribution to the heat transfer, since the fins are not contributing so much. But this is not in the scope of discussion of this webinar. Another thing to consider is, as we reduce the tube diameter for constant pitch ratios, the airflow passage depth actually reduces as well. So this can reduce the flow resistance by just reducing the path to which the air has to flow. And this is all to say that the friction resistance, which is a surface characteristic, is not equivalent to pressure drop, which is a heat exchanger characteristic. So again, we can balance out the heat transfer coefficient and the pressure drop and get benefit on both. Now, moving on to the refrigerant side of this. And if we look at the physics, they're obviously the same. We should expect actually the same kind of trend. If we reduce the tube diameter, the heat transfer coefficient is increased, also is the friction factor. But in terms of reducing channel flow, this has been studied for a while in microchannel heat exchangers, as we know, and it's been overwhelmingly proven that we actually get higher heat transfer coefficient and they're more compact heat exchangers. Now, because by reducing the flow channel, we have an increase in friction factor, ways that microchannel concepts they address the pressure drop is by having multiple distribution tubes or headers, where we reduce the mass flux on each channel and also reducing the overall refrigerant path length, so we can reduce the pressure drop within the tubes. But there are some disadvantages of doing so. We can have flow maldistribution or even additional header pressure drop, and these things are advantages of tube fin with serpentine circuits where they don't exist. On the other hand, the conventional tube fin heat exchangers, they have larger diameters, and they reduce they have reduced heat transfer coefficient, less compactness, and potentially the number of circuits may increase the mass flux and the overall refrigerant path length that may affect the pressure drop. So the idea here is that if we reduce the tube diameter, we may get the benefits from both concepts altogether. Now let's look at some numbers. So here, this is an example for a two-phase R410A with a 2.7 megapascal saturation pressure, and we're only looking at the two-phase heat transfer coefficient with different mass fluxes as we reduce the tube diameter, and similarly, we have here a pressure drop per unit length. This is just to illustrate first, as we reduce the tube diameter, we are definitely getting higher heat transfer coefficients, and we also have an impact on the pressure drop per unit length. Now, if we go back to the two concepts that we discussed in the previous slide, we have the microchannels operating all the way to this end of the spectrum with higher heat transfer coefficients, but also with higher pressure drop per unit length that is addressed by headers and multiple distribution. On the other end of the spectrum, we have large tube fin heat exchangers over here. If we move towards this direction, we're basically somewhere in between, because neither this or this spectrum end of spectrum actually is desired, and we can benefit from both if we have a tube fin heat exchanger concept that operates somewhere in between the two. Now let's quickly talk about internally enhanced tubes and why the enhancements are good. Obviously, we have the intuition of it, but first, from a fundamental aspect, let's look at a smooth internal wall tube. We have the fluid flow, and we have the thermal boundary layer. And what is interesting about this is that we see the thermal boundary layer developing here. And why do we want, why developing boundary layers are interesting? Because the actual temperature gradient at the wall, they're actually higher. So we have a local heat transfer coefficient that is much higher in a developing boundary layer than it is on a fully developed flow, where it achieves a constant value as indicated by this plot. So it is interesting to get a developing boundary layer to increase the heat transfer coefficient or even change the flow regimes. And that's exactly what the internal enhancements do. They may either develop, disrupt, and have the developing boundary layer, giving us an average higher heat transfer coefficient, and or induce the turbulence. And the turbulence, what it will do, it will promote a faster thermal transport from the wall to the core flow inside the tube. Now let's just look at a few numbers. If we look at tube enhancements, on this plot we have heat transfer enhancement factor on the y-axis. The x-axis we have equality or vapor mass fraction, and each of these plots, they indicate the tube diameter, say 3 all the way to 9.5, and the mass fluxes, which they're all the same, I think, except for this one. And similarly, we have the pressure drop penalty factor, indicated here on the y-axis of the second plot, also against equality for different tube diameters, in this case for the same mass fluxes. So what I want to illustrate here is that first, from a heat transfer coefficient perspective, the enhancement is reduced as we reduce the quality. Therefore, on a two-phase region, by increasing the vapor fraction, we get more enhancement in the heat transfer. But also, as we reduce the tube diameter, the actual enhancement also reduces. So this is 9.5, and we go all the way down here to 3 millimeters. However, if we look at the numbers, we're still getting a pretty good enhancement, even with smaller tubes. Here we have 1.5 all the way to 2.5 between 3 and 5 millimeters. So this is still pretty good enhancement overall. In terms of pressure drop, what this plot is suggesting is that the quality has probably no effect to the pressure drop itself. So it's basically flat across the quality. But also, if we reduce the tube diameter, the pressure drop penalty factor also reduces, which goes hand in hand with the reduction of the heat transfer enhancement. In this case, the 3 millimeter barely had any pressure drop penalty at all. Okay, so this was the fundamental section. So let's just summarize, the advantages that we learned from the fundamentals. From the first order analysis perspective, the smaller tube diameters gives us more compact surfaces or more area per volume, gives us less material consumption for the same area, and a smaller internal volume, which can be translated into less charge. For both the air side and the refrigerant side, the heat transfer coefficients, they increase significantly as we reduce the tube diameter at the same velocities and Reynolds numbers. On the refrigerant side as well, the unit grooves, they have the enhanced heat transfer regardless of tube diameter, so we can all benefit from it regardless if it's 3 or 9 millimeters. But now, some of the challenges and disadvantages. As I mentioned, as we saw, for both sides, we have higher friction factor, so this poses some additional design changes so we can actually reduce the pressure drop on both working fluids. And the unit grooves enhancement, they reduce with the tube diameter, though they're still beneficial. They're not as good as they are for larger diameters. So these are some of the considerations. Now, how does these things translate into a heat exchanger design and some of the considerations that we need to have? Let's go back to the friction resistance that we mentioned before, and for the air side, how can we approach it in order to reduce the pressure drop? So one way to do so is by changing the face area or enlarging the face area to reduce velocity. Although this is typically undesirable because in terms of space occupation, the face area may be more important than other geometrical aspects of the heat exchanger. But if that is a degree of freedom, this is one way to reduce the actual pressure drop by reducing the velocity and still get high heat transfer coefficients. Other ways to do is finding tube pitches that increase the minimum free flow area or reduce the flow acceleration inside the tube bundle that can increase the pressure drop as well. And we can play around with the fin density also to reduce the actual surface that is going to pose additional resistance. On the refrigerant side, one way to do so on a tube fin heat exchangers is to have more circuits. So having more circuits, we have reduced mass fluxes and overall flow length, overall path of the refrigerant, or even having shorter tubes, if that's the case. Now, on webinar number 2, which I highly encourage you all to register and attend, there are some manufacturing aspects that also need to be considered in terms of heat exchanger design, and they will actually go hand in hand with some of the design challenges from a performance perspective. And just one thing, an example here, so fin colors. So the colors are basically the extra material that we get from the fin that separate one fin and the other. If we have a very small diameter tube, the actual fin color is not long enough to actually get a good distance between the fins. So there's a minimum fin density that you need to have, and that might be an additional constraint when you're thinking about reducing pressure drop. And there are other things that with small diameter tubes might be also challenging, like tube expansion, the fin dice, types, material and thickness, and obviously we will end up with a larger number of tubes compared to conventional tube fin heat exchangers, which also mean larger number of joints. So again, this is just to highlight a few things, a few aspects of manufacturing, but please register for webinar 2 that will discuss in depth the challenges of building those heat exchangers. Now, I also like to talk about the heat exchanger design and how do we design it. And well, the idea of this is talking about correlations and their importance. So when we think about assessing the performance of heat exchangers, there are three ways basically. The first one is experimental, where we have engineers and technicians putting the heat exchanger in a wind tunnel and running the experiments and acquiring the data, reducing the data. Then we have numerical, for example, CFD, where you build a model of it, and you discretize, and you get your thermohydraulic performance out of your simulation. And lastly, we have an approximation or correlations, which are simple mathematical functions that correlate the thermohydraulic characteristics with the geometry of your heat exchangers and operating conditions. Now, if you look at from a cost effectiveness point of view, if you look at the experimental, it's obviously the most accurate way of assessing the performance of a heat exchanger, but it comes with a high engineering cost, a very high capital cost, though with a low computational cost, but it's a very time-consuming process. And if we think of heat exchanger design, that's not the most effective way of doing it so. Numerical, CFD solvers are now much more accurate than they used to be, so we can get relatively high accuracy with less engineering cost than for experimental, but still with high capital cost and a very high computational cost. And the last one is correlations, which depending on the source data, the quality of the source data, and the quality of the correlation, we can get medium to high accuracy at very low engineering cost in terms of implementing those correlations and designing the heat exchangers, very low capital cost once these correlations are available, and virtually no computational cost. So ultimately, correlations are the most effective way in assessing performance. When we are designing those new heat exchangers with small diameter tubes, we want available correlation so we can predict performance. Now, if we look at the available correlations in the literature, these are some of the selected most relevant correlations for the air side for various tubes and fin types. If you look at the applicability, none of them were actually developed for tube diameters above 6 millimeters. And why is that important? Because correlations, as I said, are mere mathematical functions that correlate two sets of data, and we have absolutely no confidence that extrapolating a correlation can give us a confident prediction if we're using a small diameter tube, for example, or if we extrapolate any of the design parameters to which the correlation was not developed for. So there was a need for novel correlations that can address basically this new design space. And recently, the University of Maryland and OTS have joined efforts, and we have now 9 new correlations for various tubes and fins, focusing on diameters below 5 millimeters. They are CFD-based correlations. So we use CFD to gather the source data, and then we have a correlation that can accurately predict the CFD simulations. And though they are not empirical, they are a very inexpensive way of predicting performance. So it gives us the freedom of not having to rely on CFD or measurements to assess the performance of tube fin heat exchangers, and giving some more power in terms of design. Refrigerant correlations. As I said before, small flow channels, they have been around for quite some time for microchannel heat exchangers. There have been several correlations developed for it. More recently, we've seen some new developments for internally enhanced tube with small diameter tubes, as indicated here in the table. And basically, with both sets of correlations, that gives us enough tools to create and optimize novel heat exchangers. Now, the importance of correlation validation, though we have the correlations, which gives us a very good guidance on which direction to go, we're still going to end up having to validate them once we have a new design. And this is just an example of a correlation validation where we tested the heat exchanger for a louver fin using the louver fin correlation and a small diameter tube correlation. In terms of capacity, we got a pretty good agreement, plus minus 3%. The refrigerant side correlation for pressure drop predicted plus minus 20%. But what is interesting is to see that the air side pressure drop was within 10%. And though the correlation is CFD based, it was pretty encouraging to see how good the prediction was compared to the experimental results. So one thing that I want to bring to this program is also the importance of tuning the correlations and making our tools more accurate and more precise. So we obviously need always additional experimental data for correlation verification and validation. And this could be an opportunity for collaboration. So for those who are interested in having a heat exchanger, a sample of heat exchanger to test in your facility, we can share the data, do cross-validation with multiple sources. This strengthens our correlations and the accuracy. We're going to have a large database with access from everyone involved, and this can lead to several new publications potentially. Like I said, we have these correlations, and these are the essential tools for performance prediction. And there are several platforms or software that you can basically put these correlations and build your heat exchangers or design your new heat exchangers. We're obviously going to talk about the Coil Designer, which is developed by UMD and OTS. This is just an introduction to it. Please register for webinar 3, where we're going to actually give a demo on it, on its features and how to design a heat exchanger with small diameter tubes, and provide some examples of heat exchangers that we designed using Coil Designer, and they were validated once we had a prototype and tested. So this is a very powerful tool and computationally inexpensive, so to say. So let's go to our last section, which is the applications. And I said here we have three case studies, and all of them obviously using our design tools or our new correlations and Color Designer to optimize performance and other aspects of the heat exchanger. So the first study is surface optimization only, where we're maximizing heat transfer and minimizing, maximizing heat transfer coefficient and minimizing pressure drop on tube feed heat exchangers with different diameters. And the second one is an actual application for a split condenser optimization, where we use new correlations and Color Designer to optimize this heat exchanger, targeting minimizing the air side pressure drop, the raw material cost, and the refrigerant charge. And the last one is a study also on a window AC condenser, where we were focusing on improving the system's performance, reducing cost and refrigerant charge. So the first study, as I said, it was several optimizations targeting maximizing heat transfer coefficient and minimizing pressure drop for different diameters. So what we're seeing here on this plot are 3 Pareto fronts for different diameters, 3, 4, and 5 millimeters. And the table indicates a few points from these plots. The first one, what I'm showing here, is a 7 millimeter surface. And as we can see, from a heat transfer and pressure drop perspective, as we reduce the tube diameter, we go all the way up. So we can, this is another verification of how reducing the tube diameters gives us a significant improvement in surface performance. The table also shows the end points in the Pareto front for the 5 millimeters, but most importantly, we have here these 3 points, one from each Pareto set with similar pressure drop. And what we are showing is that for similar pressure drop, we actually improve or increase the heat transfer coefficient as we reduce the tube diameter. So this is another verification, not only that the heat transfer coefficient increases, but not necessarily the pressure drop has to increase as well, though we get higher friction factors. So this study was published last year at the Purdue conference. It's available online, and I think we also made it available, I'm not sure. The second study is a split condenser optimization, as I said before, targeting minimizing the air side pressure drop and the raw material cost. So we have actually 2 sets of optimizations, and the other one is air side pressure drop and refrigerant charge. And these are all the Pareto fronts for each tube diameter size, from 3 all the way to 9.5. So the 3 is here, the 9.5 is over here. And what is interesting to see is what is the potential improvement or the potential that we get out of this. From this study, what we're showing is that from both optimizations, the maximum pressure drop reduction we got is around 60% if we compare 9.5 with a 3 millimeter or even a 4 millimeter, 5 millimeter. B indicates the raw material cost. This is basically reducing 74% of the material between this heat exchanger and this heat exchanger. And again, all of these designs, they're delivering the same heat capacity. So this is pretty interesting to see how much less material is required to do the same job. And lastly, we have the refrigerant charge. Here we have a potential of up to 90% of refrigerant charge reduction within the heat exchanger. Now again, we need to remember that this is a charge reduction inside the heat exchanger. It does not mean that you're reducing the overall charge of the system, because we're not changing other components, including connection tubes, connection pipes, the compressor, or in this case, even the evaporator. But a significant reduction in charge in the condenser will obviously lead to a reduction in charge in the system. Now, the last study is a window AC condenser as well, focusing on COP improvement, material reduction, and charge reduction. And here we have on this table a baseline and 3 novel designs using small diameter tubes with different fins. And we can see from 20 to 50% reduction in material, 10 to 50% reduction in refrigerant charge, while still improving the overall system COP in up to 6 to 7%. Now, the interesting thing about this study is that this particular heat exchanger, we have experimental data for it, and it ended up reducing the overall system charge in about 10%, while also increasing the COP in actually 4%, not the actual 6%, but still increasing the COP and reducing the cost by approximately 40%. So this is a pretty amazing improvement just by replacing the condenser with a small diameter tube design. So the take-home messages include small diameters. They are more compact, they require less material, and they will lead to less refrigerant charge. They will yield much better heat transfer coefficient, though with higher friction factor. Copper tubes, they have low thermal resistance. They can withstand high pressures with less material. They have some additional benefits that might not necessarily be used in every design, such as corrosion, biofouling resistance, and intergrooving the copper tubes is pretty much straightforward. Design tools. Correlations are the most effective way of assessing performance, as we saw before, but there's still a need for experimental data for tuning and modifying these tools so we can have more accurate and precise tools that everyone can use and get even better designs. And just to summarize the improvements that we actually obtained with novel heat exchangers, from a surface perspective, 3 millimeters had 70% higher heat transfer coefficient than a 5 millimeters at the same pressure drop. A 60% pressure drop reduction in a condenser with 75% reduction in material and 90% in charge. And in the whole system analysis, when replacing the condenser, we also got 10% less charge in the system, 4% more COP, and 40% cost reduction. So this concludes this webinar. Please register for webinars 2 and 3. The second one is construction of small diameter copper tube feed heat exchangers. We'll address the manufacturing aspects of this. And the webinar 3 is the effective design of small diameter tube feed heat exchangers using our tool, Coil Designer. And again, this presentation will be made available to you tomorrow, along with a recording of the presentation and a feedback survey, and that we highly encourage you to fill out and send it back to us. And again, for those who arrived in the middle, I mentioned in the beginning, if you're interested in having a sample heat exchanger to your facility, delivered to your facility, we require that you attend all 3 webinars and fill out all the feedback survey forms. So I'd like to thank you so much for your attention, for your time. Here's our contact information. Now we're going to read some of the questions that you guys put on you typed here on GoToMeeting, but you're more than welcome to send us an email if you have further questions or comments or something that you want to discuss. Sorry, I'm reading here the question. So the first one, let me just repeat the question for everybody to hear. So the first one is, can this be applied to air-water heat exchanger as well? Well, absolutely. You know, in particular, because this is regardless of the working fluids, and if you have water, you have in single phase, usually the thermal resistance of the air is even more important on the air side, and by reducing the tube diameter, you have significant benefits as well. So this application can be benefited in air to water or air to refrigerant can benefit from reducing the tube diameters as well.
You go ahead and read through that. I'll answer this. So we received another question
indicating that a lot of the studies we show here are focused on condensers, and that's true. And asking whether or not we've looked at evaporators in these types of studies. So I can say that some of the refrigerant side correlations that Daniel highlighted are valid for evaporators for these small diameter tubes. So those design tools do exist for you. And then the air side correlations that we've shown would also be relevant. But when we look at evaporators, we certainly have to consider the wet condition where the surface may be covered in a film of liquid. So the correlations that we've shown here, these new CFD-based correlations, are specifically developed for the dry condition. So we would expect that when we do experiments of evaporators in the wet condition, we would see some variation there from the accumulation of condensation on the fin surfaces. We've done a few experiments with both 5 and 4 millimeter evaporators, and we've seen fairly good agreement with the predictions that the correlations give. But there is some discrepancy in terms of the sensible and latent heat load that requires some additional research. But nevertheless, I think the correlations are certainly valid for these types of heat exchangers as well. Just this one.
Well, we have a few more minutes. If anybody has any questions, please feel free to type in, or you can also contact us later on. These were the questions that we got so far.
So there's one more question regarding the window AC system that we looked at, and in this situation we were looking at a heat exchanger that was about a 7.5 millimeter tube, and reduced that down to a 5 millimeter tube. The tubes are internally enhanced copper tubes, and the fins that we replaced them with were split fins, and we also explored louver fins. The result that was actually shown with the savings that we presented, that was a louver fin 5 millimeter heat exchanger that was dropped in to replace that baseline 7.5 millimeter heat exchanger. So there's another question about the effects of increased refrigerant pressure drop on overall system performance, and I think it speaks to a concern when we look at these smaller diameter tubes that when we implement something like a 5 millimeter or smaller heat exchanger, that we're going to have to suffer with this consequence of increased refrigerant side pressure drop, and that can be problematic on overall system performance, and that's certainly a valid concern. And especially on the evaporator side, when we have excessive pressure drop, that can be a challenge. On the condenser side, the concern is a little bit less. But in any case, I think what we've found so far in designing these heat exchangers has been that with proper design and circuiting, we can overcome these challenges and design heat exchangers that don't have a refrigerant side pressure drop that is increased to the detriment of the system performance. So as far as what have we tested, we've developed a couple of systems in-house that have 5 millimeter heat exchangers, and in all of those cases, we haven't seen a major consequence in terms of COP reduction or capacity reduction due to the refrigerant pressure drop. But that's mostly because we designed these systems, to have the number of circuits that's required to ensure that we don't have excessive pressure drop. Hopefully that's helpful.
So let me just add to that quickly. So what we discussed before is basically highlighting that small diameter tubes, they have higher friction factor, and therefore we need to tackle the design approach so we don't have higher pressure drops. And that was the whole point, that we can actually do things such as increasing the number of circuits or reducing the tube length, so we don't have the actual higher pressure drop, even reducing the tube diameter. So it does not imply that by reducing the tube diameter, we will end up with higher pressure drop on both fluids in our heat exchanger designs. So in our optimization projects, what we do, we constrain the pressure drop exactly not to exceed our baseline pressure drop on both working fluids.
So there was one question about the details of the fin pattern that was used for the AC optimization. I know that this was a commercially available fin pattern that was chosen, but I think for confidentiality reasons, I won't go into that. And furthermore, I don't think I remember the exact dimensions of this, but it was a standard size tube stagger pattern for the louver fin, 5 millimeter. And I imagine you're aware on the market there aren't a whole lot of patterns available, so that size range is fairly typical. Can you see the next one?
Are there any correlations that support the argument of increase in the heat transfer rate when using grooved corrugated tubes?
Yeah, so when we're in the single phase region, I think there's a number of correlations that do characterize the heat transfer performance of liquid water or liquid fluids flowing in a enhanced grooved or corrugated tube, and there are certainly conclusions that the heat transfer is enhanced in those cases. The cases that we showed in this presentation are all specifically looking at the two-phase region, just to kind of put a little more focus on the HVAC industry where the two-phase heat transfer is dominant, but in water applications, there is also enhanced heat transfer due to that enhanced surface inside of the tubes. The correlations, I think, I don't know that they were summarized in here. I think we only included two-phase heat transfer correlations, but within our software and within the literature, you can find a number of correlations for single-phase heat transfer inside a small diameter internally enhanced tubes that would give you be able to characterize the performance inside of them, and they would illustrate that the heat transfer is typically higher in an enhanced tube than a smooth tube. Okay, so that's all the questions we've received so far. I guess we can kind of put this up as a last call for any additional questions. And of course, you can follow up with us by email after the session's over with any other questions you might have. Just give it a few more minutes in case anyone has additional thoughts.
Tomorrow, the presentation, the recording, and the feedback survey form will be available to you probably around noon Eastern Standard Time. You're welcome. Well, I guess we're now 5:02, so we will end our webinar session. Again, I encourage you, those attending, to register for webinars 2 and 3 that will happen next month and the following. And please, I encourage you to fill out the feedback survey. And also, if you're interested in a sample heat exchanger, let us know and send us the survey forms. Thank you so much for your attention, for participating in this program. Hope to see you soon.